In the last lecture, we discussed vector spaces. These are sets with two operations, addition and multiplication by elements of a field. Today, we are going to talk about subspaces. So these are subsets in vector spaces that are vector spaces themselves. So let's give a definition. So let V be a vector space. Over a field F. So definition. A subset U in V is called a subspace if it satisfies three properties. 1. Zero vector, well, V is a vector space, so it contains a zero vector, belongs to this subset U. 2. For all U and V in U, we have U plus V also in U. So this means that this subset must be closed under addition of vectors. So if we have two vectors in this subset, then their sum is also in the subset. And 3, for all U in U and all scalars C in F, C times U is also in U. So this means that this subset is also closed under multiplication by scalars. So if we take any vector from this subset and any scalar, then this scalar multiple of this vector is also in the subset. Let's give a couple of examples. So in the first example, so let's take V to be R2. So this is a plane with a coordinate system. And as a subset U, so let's take a line y equals x. So this line passes through the origin. And so here in this example, V is a coordinate plane, and U is a line y equals x. So we can see the vectors with a starting point in the origin and the end point on this line. So we claim that this subset U satisfies properties 1, 2, and 3. So let's check this. So zero vector. So zero vector is the vector that connects origin with itself. So clearly it's on this line, so property 1 will hold. So zero vector is in this subset. Then, so property 2 says that if we take two vectors in this subset, right? So this means that we take two vectors on this line. So one like this, and another could be same direction or opposite direction. So if we add two vectors that are both on this line, the resulting vector will also stay on this line. And so what we see is that the second property holds. And for the last property, so if we take a vector on this line y equals x and multiply it by a scalar, so this means that we rescale this vector, then the resulting vector is still on this line. So this means that this subset is closed under addition, closed under multiplication by scalars, and contains a zero vector. So this means that this line is a subspace in this coordinate plane. A second example is similar in nature. So let's take V to be R3. So this is a three-dimensional space with a coordinate system. And so here, so we can draw the three coordinate axes, and as a subset, I'm going to take a plane that passes through the origin. So U is a plane passing through 0, so the origin. So we claim that U is a subspace. So U is a subspace in R3. So indeed, so let's look again at the properties of a subspace. So 0 vector is in this subset. Well, so here we declare that this plane passes through the origin, so 0 vector is in this plane. Then property 2 says that if we take two vectors in the subset, then their sum is in the subset. So here, if we take two vectors on this plane, then their sum is defined by the parallelogram rule. But if we have two vectors inside this plane, then this parallelogram is also going to be inside this plane. And the sum of two vectors is given by the diagonal of this parallelogram. So clearly the sum is going to be inside this plane. And so property 2 will hold. And likewise property 3. So if we take a vector on a plane that passes through the origin and rescale this vector, so multiply it by a scalar, then rescaled vector will still be inside this plane that passes through the origin. And so this means that all three properties hold, and this plane inside R3 is going to be a subspace. Let us mention some elementary properties of a subspace. Let U be a subspace in a vector space V over a field F. Lemma. One. If a vector U is in the subspace, then the opposite vector minus U is also in a subspace. 2. If we have two vectors in the subspace and two scalars in the field, then a linear combination C1U plus C2V belongs to the subspace. Let's give a proof of this lemma. We start with part 1. So we assume, so suppose U is a vector in a subspace U. Then by property 3 of definition, we have minus 1 times U is also in the subspace, right? So here we know that if we have any vector in a subspace and any scalar, then this scalar multiple of a vector is going to be again in the subspace. But by our exercise, so by exercise from last time, we have minus U is the same as minus 1 times U. So this implies that minus U is in the subspace. And that's exactly what we had to prove, right? So for any vector in U, the opposite is in the subspace. And for 2, so we start with 2 vectors in U. And again, by property or by part 3 of definition, so we have C1U will be in U, and so will C2V. So these 2 vectors will be in U. Right. So if we have 2 vectors in U, then their scalar multiples will be in the subspace U as well. But then, by property 2 of definition, so their sum is also going to be in U. So we have C1U plus C2V is in U. And that's what we need to show here. So what we obtain is that if we have 2 vectors in the subspace, then their linear combinations are also going to be in the subspace. Let us mention another important property. A subspace U in a vector space V over a field F is itself a vector field, a vector space over F. Now, so what does it mean? So a vector space is a set with the following operations. So it has addition of vectors, it has multiplication of vectors by scalars, it has a 0 vector, and it has the opposites of a vector. So we have this unary minus operation. Now, if we have a subspace in a vector space, then by definition of a subspace, it's closed under addition. So this means that we can define addition on this subset. It's also closed under multiplication by scalars. So this means that on this subset, we can define multiplication by scalars from the field. It contains a 0 vector. And by property 1 of this lemma, it also has the unary minus operation. So this means that a subspace has all prerequisites of being a vector space. So it has all the operations of a vector space. Now, a vector space must satisfy 8 axioms that are reasonable axioms like U plus V is equal to V plus U and so on. Now, do we need to verify these axioms for a subspace to check that it's a vector space? And the answer is no, because we know we're given that V is a vector space. So this means that all the properties that we need are satisfied in V. And in particular, they're satisfied for vectors from U, because U is just part of a larger vector space. So this means that to see that a subspace is a vector space, we only need to make sure that the subset is closed under the operations of a vector space. And then all the 8 axioms of a vector space will come for free, because they are just inherited from the parent vector space V. To build our intuition about subspaces, let's go through several examples and decide whether the following subset is a subspace or not. So as our first example, so let's take U to be a subset in R2, so a plane with a coordinate system that consists, so U consists of vectors OP, where O is the origin of the plane, and P belongs to the line x plus y is equal to 1. Let's make a picture. So here we have a coordinate plane, and so here we have a line x plus y is equal to 1. So the slope of this line is -1, because it can be written as y equals 1 minus x. And so the intercepts are both equal to 1. So this means that the set of vectors that we consider are vectors that have initial point at the origin, and the endpoint runs over this line. So this line is our subset U. Now, is this subset a subspace? So does it satisfy the three properties of a subspace? And here we start with the first one. So it's when we have a question like this, the easiest property to decide is whether 0 belongs to U or not. So is 0 vector in U? And here we see that the answer is negative. So that if we take a 0 vector, so which is connects origin to itself, the 0 vector is not on this line. And so the answer is negative. And for something to be a subspace, it should satisfy all three properties of a subspace. If any one of these three properties fails, then this subset is not a subspace. And here the first property failed right away. And so the conclusion is that this U, this line x plus y is equal to 1, is not a subspace. Let's consider another example. So suppose V is again R2, so it's a vector space over R, and U is the set of all vectors xy with the property that x is greater or equal to 0 and y is greater or equal to 0. Right, so let's just recall that these curly parentheses mean that we're forming a set. So here, before the vertical bar, we write down what are the objects of this set. So these are two-component vectors from R2, x, y. And after the vertical bar, we write down the defining properties of this set. So we take only vectors with the non-negative components. Now, we want to decide whether this subset is a subspace or not, right? And so geometrically, so this is a quadrant on a coordinate plane. Right? So this is our subset U. Now, let's go through the properties. So here, so the first property of a subspace is that 0 must belong to U. Now, what's 0 vector here? So 0 vector in R2 is a vector with two components 0. And indeed, it meets the criteria here. So the components of this vector are non-negative. So this means that this property holds. So this is true. The second property is closure under addition. So if we have x1, y1 in U, and we have x2, y2 in U, is it true that their sum, and the sum is going to be x1 plus x2, y1 plus y2. Is it true that this is in U? Now, for these vectors to be in the subset, so their components must be non-negative. And so if all these four numbers, x1, x2, y1, y2 are non-negative, then the components of this vector are also going to be non-negative, because the sum of non-negative numbers is non-negative. So this means that this property also holds. Right? So this is true. So the second property of a subspace will hold. Now, how about the third property of a subspace? So if we have U, a vector in the subset, in this first quadrant, and C is a real number, is it true that C times U belongs to this subset? Right? So if we take a vector in this quadrant and rescale it, is it true that the resulting vector still in the same quadrant? And so here, so what we see is that this will be true if C is greater or equal to 0. But this false if the scale is negative. So if we take a vector with non-negative components and multiply it by a negative scalar, so the result will be a vector with non-positive components. So if we take, so for example, so if we have U to be a vector 1, 1, so that's in U. And if we take C to be negative 1, so that's a real number. So we have minus 1 times U is not in U, right? So because this is a vector minus 1, and it does not satisfy the defining property of U. It's sufficient for the properties to fail in a single instance. And if one property fails in a single instance, so this means that the properties of a subspace do not hold in general for this subset. And so conclusion is that U is not a subspace. Let us try to fix the previous example. So let's make now a larger set where we take vectors on a plane that have either non-negative components or non-positive components. So this means that either both are non-negative or both are non-positive. So geometrically, this will mean the following set. So we still include what we had before, but we also include the third quadrant of the plane. Right? So now let us decide whether this larger set is a subspace or not. Right? So the first property is zero vector. Is it in U? Check. Yes, it is. Right? So it clearly satisfies these properties. Now, our third property that gave us trouble before, so if we take U in U and C in R, then C times U is in U, right? And here, this property will also hold. And so here we will have to consider different cases. So we can have U in the first quadrant and C positive. Then clearly that if we take a vector in the third quadrant and rescale it with the positive scalar, then the result is still in the first quadrant. If C is negative, then rescaling a vector from the first quadrant will get a vector in the third quadrant, but that's also included. And similar for vectors that are in the third quadrant. So when we try to rescale them, the result will be still in this subset. So this third property now holds. Now, how about addition of vectors? Now, is it true that if we take two vectors u and v in this subset, then, with a question mark, the sum is in subset, right? So if we take two vectors with both components non-negative or both components non-positive, is it true that their sum will still satisfy the same properties? So now this is not quite obvious, but it turns out that the answer for this is negative, right? And here we'll have, if we take one vector like this and another vector like this, then by parallelogram rule, the sum will be here, and that will clearly bring us outside of this set, right? And so we can give an example. So we take u to be 3, 1. That's certainly in u. And as v, let's take -1, -3. That's also in u. Now let's consider the sum of these two vectors. So we have 3, 1 plus -1, -3. So the sum of these vectors is going to be 2 here, and here we have -2. So what we've got is we've got mixed components. One component is positive and another is negative. So this means that this is not in U. And so this tells us that in general, this property fails, right? So because this property has here, it's postulated that this property should hold for all u and v in the set U. The sum must be in U. And here we found an example of two vectors that are in U, but their sum is not in U. So this means that not for all u and v in U, the sum is in U. And so this means that this property fails. By the way, so in mathematics, we use for all expression very often, and we have a special notation for this. So instead of writing for all, say, u in U, so we write this symbol, and this symbol stands for all u in U. So this is a shorter mathematical way of writing the expression for all. So this symbol is called universal quantifier. And so it reads, so this is a flipped letter A, and it reads for all. There is a second quantifier, which is written like this. So this is a flipped letter E. So this is called existence quantifier. And so when we read this, so this means there exists. So this is another notation which is commonly used in mathematics. Let's give more examples of subspaces. So suppose now V is Rn. So this is a vector space of n tuples with real components, and it's a vector space over R. And fix some non-zero vector V in Rn. And take U to be all multiples of V. So TV, where T runs over R. So geometrically, this is a line in Rn through the origin and with directing vector V. So we claim that this is a subspace. So indeed, so the first property of a subspace, so we need to see that 0 belongs to this subset U. But to see this, so we just take t equals 0, right? So these multiples, so we take multiples of v for all real t. And in particular, one of these elements of this set is when we take t equals 0. And so this tells us that 0 times v, which is a 0 vector, is in our subset. And so this means that 0 vector belongs to the subset. 2. So if we have 2 vectors in this subset, right, so then they will be written as t1v and t2v, right? So then we need to see that their sum, so what's their sum? t1v plus t2v. So this can be written by distributive law axiom of a vector space. This can be written as t1 plus t2 times v. And what we see is that the sum of 2 multiples of v is again a multiple of v. And this belongs to our set U, because our set U consists of all multiples of v. So this vector is in U. So the sum of these 2 vectors is in U as well. And the third property, so if we take U in the subset and scalar to be a real number, then we need to verify that scalar multiple of U is in U. So we need to check whether C times U is in U, right? So, but if U belongs to this subset, so this means that there exists T in R such that U is equal to T times V, right? So because our subset consists of all multiples of this vector V. So then C times U is the same as C times TV. But again, by one of the axioms of vector space, this is the same as C times T times V. And C times T is a real number. So what we see is that this is a scalar multiple of a vector V. And so this is an element of the set U. So we conclude that all 3 properties of a subspace hold here. And so this means that, so conclusion is that U is a subspace. Let's try to construct the analog of this example, but now not over real numbers, but over a finite field. Let's, as V, take the space of bytes. So this is Z2 to the power 8. So this means that these are 8 component vectors with entries from Z2. And let's take V to be one particular non-zero vector from this space. So let's take 1, 1, 0, 0, 1, 0, 0, 1. Now, what we want is we want to take U to be a line through V, or so a line with this directing vector. What does it mean? So what does it mean to take a line in the space of bytes? Well, the definition is going to be very similar to this one. So U is going to be the set of T times V, where T, now V is this particular byte, and T, well, of course, T cannot run over real numbers. So T runs over our field Z2. Right? So in this example, the field is Z2. Now, what kind of set this is going to be? So in fact, because T runs over Z2, so there are only two possible values for T. So T could be 0 or 1. And so this set can be written explicitly very easily, right? So if T is equal to 0, then the result is 0, right? So if we take this byte and multiply it by 0, we're going to get a 0 byte. And if T is equal to 1, then 1 times this byte is this byte itself. So this set of two vectors is a line in this space. So this is a line in Z2 to the power 8. So this is how lines look like in the space of bytes. And we claim that this, so U is a subspace in Z2 to the power 8. So let's go through the axioms of a subspace. So here, 0 vector belongs to this subset. That's true. Now, this subset must be closed under addition of vectors. And additions are carried out mod 2. And again, we see that this is true. If we take 0 plus v, that's v. And if we take v plus v, but so because over Z2, 1 plus 1 is equal to 0, and 0 plus 0 is equal to 0. So if we add this byte to itself, then we're going to get a 0 byte. And so what we see is that this set is closed under addition. And it's also closed under multiplication by scalars, because scalars here are in Z2, and there are only two possible scalars. So it's 0 or 1. And clearly, if we multiply anything by 0, we get a 0 vector. And if we multiply anything by 1, we get itself. So this means that this set is closed under multiplication by scalars. And so we conclude that this set of two elements is a subspace in the space of bytes. In our next couple of examples, we'll go to the other extreme. Instead of considering very small vector spaces, let's consider very big ones. So let F be the space of functions from real numbers to real numbers. So these are real valued functions with a real argument. And we take all such possible functions. Right? So here we treat functions as vectors. And this is a vector space, as we have seen in the previous lecture, because we can add functions. So the sum of two functions is again a function. And we can multiply a function by a real number. So this means that this set of all such possible functions is a vector space. And we take U to be R of x. Right? So these are polynomial functions. And we claim that U is a subspace in F. So let's indeed check this. Well, what's a 0 vector in F? 0 vector in F is a constant 0 function. So it's a function that assumes 0 value for all x. And constant 0 is a polynomial function. So this means that 0, which is a constant function, so f of x is equal to 0. So this is in U. Then, so for the second property of a subspace, we have the following, that a sum of two polynomials is a polynomial. And so this means that this set U is closed under addition. So U is closed under addition. And the third property here will also hold. So if f is a polynomial and c is a real number, right? So we should say that, of course, f is a vector space over a field f of real numbers. And so coming back here, so if we take a polynomial and a real scalar, then so what we have is that c times f is also a polynomial. So what we see here that all three properties hold, and so the space of polynomials is a subspace in a vector space of all functions. And of course, this subspace does not coincide with the whole space, because there are functions that are not polynomials. So, for example, sine of x. So it's a function from f, but not from this subspace. For the next example, I will assume some familiarity with calculus. So let f as here, so be the vector space of functions f from R to R. And as U, so let's take the set of continuous functions. From real numbers to real numbers. So this will include all the polynomials, but also sine function, sine of x, also will be in this subset. Then what we say is that U is a subspace in F. Now, what does it mean to verify these properties? So property 1, zero vector is in U. So what does it mean? So zero vector here is a zero function, right? So this is a constant zero function. So f of x is equal to 0 for all values of x. And this function is continuous, because a constant function is continuous. So this means that this property holds, so that zero vector is in U. The second property is based on the following theorem from calculus, that the sum of two continuous functions is continuous. So if f is a continuous function and g is a continuous function, then f plus g is a continuous function. And so this implies that if f and g are in U, then f plus g is also in U. And so what we have is, we have the second property of a subspace also holds. And 3, so this also follows from calculus. So if f is continuous, then c times f is continuous. And so this means that this subset U is closed under constant multiples, right? So if we take an element from U, so this is a continuous function, and if we multiply it by any real number, the result is a continuous function. And so this means that this subset of continuous functions is satisfies all three properties of a subspace, so it's a subspace. And now let's come back to polynomials. So now, as a vector space, let's take polynomials R of x. So this is a vector space over the field of real numbers. And as a subset, so let's take polynomials of degree at most 2. So polynomials of the form ax squared plus bx plus c, where a, b, and c are real numbers. So we claim that this subset is a subspace in the space of all polynomials. Now, first property is that 0 belongs to U, right? So here this is true because 0 polynomial is the same as 0 times x squared plus 0 times x plus 0. And so here a, b, and c run over real numbers. So this means that this polynomial that's on the right-hand side is in U, but this polynomial is a 0 polynomial. So this means that 0 vector is in U. 2. So if we take 2 vectors in U, so U and V are in U. So what does it mean? So this means that the first vector can be written as a quadratic polynomial with coefficients a1 x squared plus b1 x plus c1. And V is also in this set, so this means that a polynomial V also satisfies the same pattern. So it's a2 x squared plus b2 x plus c2. Then we take the sum, u plus v. And so what's the sum? So it's going to be the sum of these two polynomials. So a1 x squared plus b1 x plus c1 plus a2 x squared plus b2 x plus c2. But this sum of two polynomials can be written as a1 plus a2 x squared plus b1 plus b2 x plus c1 plus c2. And what we see is that this result conforms to the pattern that determines the set U. So this is in U. And that's what we had to prove. So that if we take arbitrary 2 vectors in U, then their sum is again in U. That's what we see here. And part 3 here for scalar multiples, I leave it for you as an exercise. So verify the third property of a subspace. So what we get here is that this set of quadratic polynomials forms a subspace in the set of all polynomials. For our next example, we take V to be the space of 2 by 2 matrices with real entries. So these are 2 by 2 matrices with real entries. So we saw in the last lecture that this is a vector space because we can define addition of matrices component-wise, and same with scalar multiplication of matrices. And as a set U, let's take the following subset of matrices. Let's take matrices of the form A, B, 0, C, where A, B, and C run over real numbers. So these are sometimes called upper triangular matrices. So they have 0 in the lower left corner. So we claim that this is a subspace. And to check this, so we take 0 vector. So what's a 0 vector in this vector space? A zero vector is a zero matrix, 0, 0, 0, 0. And we see that this zero matrix conforms this pattern if we take A, B, and C to be all zero. So what we see that this belongs to U. And so the first property holds. The second property, so if we take U and V, two vectors in this subset, then U may be written as A1, B1, 0, C1, and V can be written as A2, B2, 0, C2 for some A1, B1, C1, A2, B2, and C2. Then what is U plus V? U plus V is the sum of these two matrices. So it's A1, B1, 0, C1 plus A2, B2, 0, C2. But what's the sum of two matrices? The sum of two matrices is carried out component-wise. So we get A1 plus A2, B1 plus B2, 0, C1 plus C2. And what we see is that the result is again in our subset, because the result again has 0 in the bottom left corner. So this means that the resulting matrix conforms the same pattern, so it is in the subset U. And so we see that the second property of a subspace holds. And the third property of a subspace, again, I will leave it for you as an exercise. And we will conclude that this subset of upper triangular matrices is in fact a subspace in the vector space of all 2x2 matrices. Our next pair of examples are extreme subspaces that can be taken in any vector space. So here, so let's take V to be any vector space. And let's take U to be a subset that consists of a zero vector. Then, so this is what we call the zero subspace. And indeed, so it will satisfy all properties of a subspace. So it contains a zero vector. It is closed under addition because the sum of a zero vector with itself is a zero vector. And it's closed under scalar multiplication because a scalar multiple of a zero vector is a zero vector. So all properties of a subspace will hold, and so we have a zero subspace. Another subspace that we can construct, which is also not very interesting, is V itself is a subspace in V. So we can take the whole set as a subset, and then clearly it will satisfy all properties of a subspace because it's closed under all operations of a subspace. So here, this will be two extreme examples of subspaces. So we can take the smallest possible subspace, which consists of a zero vector, and the largest possible subspace, which is the vector space itself. We have a special tool for constructing subspaces. So this tool is called the span. So let's give a definition. Let S be any subset in a vector space V over a field F. So we do not require that S to be a subspace. So it's just any subset. And we define span of S as a set of all possible linear combinations of the following form. So we take C1 V1 plus C2 V2 plus CK VK, where all vectors V1 through VK belong to S, right? So we take vectors from this given set S, and the scalars C1 through CK belong to our field F. So we take all possible linear combinations of vectors from S with coefficients from the field. And here K is arbitrary. And so then this set is called span of S. And we have the following important theorem that says that for any subset S in a vector space V, span of S is a subspace in V. So, in other words, span is the construction that takes any set from our vector space and creates a subspace in this vector space. And so let's give a proof. So we need to verify, so we take U to be span of S, and we need to verify the three properties. So we need to verify three properties of a subspace. To check the first property, we can set all CIs to be 0. So if we take a linear combination with 0 coefficients, then this tells us that 0 vector will belong to the set U, right? So a linear combination with all 0 coefficients is equal to the 0 vector. And so this tells us that 0 vector always belongs to the span. 2. Suppose we take two vectors from the span. So suppose U and W belong to the span of S. So what does it mean? So this means that U can be written as C1 V1 plus CK VK, where all VI's belong to the set S. And W can be written as D1 V1 prime plus dr VR prime, where these vectors Vj prime are also in S. So these vectors, the prime vectors, could be the same or could be different from V vectors, as long as they're all elements of the set S. And then from here we see that U plus W is just a longer linear combination. So it's C1 V1 bar plus CK VK plus D1 V1 prime plus dr VR prime. But what we have is all vectors V's and V primes are all in S. So this means that this is still a linear combination of vectors from the set S. And so this linear combination belongs to span of S. And so we conclude that if we have two vectors from the span of S, then their sum is from the span of S. And the third property, again, I leave as an exercise. Let me assign you the following exercises. So consider some of the subspaces that we discussed today, right? So first, we have a line y equals x in R2. 2. We had, so U was the space of matrices A, B, 0, C in M22 of R. And 3, we had U was the set of ax squared plus bx plus c, where A, B, and C is in R. So this was a subspace in the space of polynomials. And for each example, find a finite set S such that U is span of S. So in each of these examples, find a finite set of vectors in the vector space in question, right? So here, this will be a subset of R2. Here, this subset will be the subset in the set of matrices. And here, this subset will be the subset in the space of polynomials, such that the span of this finite subset is gives precisely these subspaces. So in agreement with this theorem. So this theorem says that any span is a subspace, but here we're trying to do the opposite. So for a given subspace, we want to realize it as a span. And one more exercise. Show that span of S is the smallest subspace in V containing subset S. So in other words, so equivalently, if U is a subspace in V and U contains S, then U contains the span of S. Now let us talk about subspaces in Fn, so where F is an arbitrary field, and systems of linear equations. So first we begin with the definition. A system of linear equations AX is equal to B is called homogeneous if the right-hand side column B is equal to 0. So this means that we have a system of linear equations with all right-hand sides being 0 scalars. So in this case, such a system is called homogeneous. We have the following important theorem about homogeneous systems of linear equations. So let AX equals 0 be a homogeneous system of linear equations over a field F so meaning that all coefficients in the coefficients matrix come from the field F, and unknowns also I assume to have values in F with n unknowns. So this means that X here is the column x1, x2 up to xn. So then its set of solutions U. So we take all set of n tuples in F that satisfy this system of equations. And so this will be the set of solutions U, is a subspace in Fn. So solutions will live in the space of Fn. So solutions are n tuples with entries in the field F. And we claim that this set of all solutions forms a subspace in Fn. And here it's important that the system is homogeneous. So this result does not apply to non-homogeneous systems of equations. So let's give a proof. So here, we need to show that 0 vector, which is a 0 n tuple, is in U. So what does it mean? So this would mean that this n tuple is a solution of AX equals 0. But here, if we substitute x1 equals 0 and up to xn equals 0, so if we substitute all variables to be 0, then clearly, we get a solution. Because if we make the substitution, the right-hand side will clearly be 0. And so this implies that 0 vector is a solution. And so this means that 0 vector contains in U. Now, for part 2, we take 2 vectors in U. So U and V are in U. So let us write them down. So U is a column S1 through Sn, and V is a column R1 through Rn. So what does it mean that these 2 vectors belong to U? So this means that U and V satisfy all equations of this system of linear equation. In particular, let's take equation number I. So what does it mean that U satisfies equation number I? So this means that AI1 S1 plus AI2 S2 plus AIN Sn is equal to 0. What does it mean that V satisfies the same equation? So this means that AI1 R1 plus AI2 R2 plus AIN Rn is equal to 0. So what do we need to show here? We need to show that U plus V is in U. So what does it mean? So what's a vector U plus V? U plus V is a vector which is the sum of these two vectors. S1 plus R1, S2 plus R2, Sn plus Rn. What does it mean that the sum of U plus V belongs to U? U is the set of solutions of the system of equations. So this means that we need to verify that the vector U plus V is a solution of the system of linear equations Ax is equal to 0. So let us verify that U plus V is a solution of Ax is equal to 0. Now, take equation number I. So, and substitute this n tuple in this equation. So we have AI1 S1 plus R1 plus AI2 S2 plus R2 plus AIN Sn plus Rn. But this can be written as a sum. So this is equal to AI1 S1 plus AIN Sn plus AI1 R1 plus AIN Rn. However, we knew that U and V were solutions. So this means that U and V satisfied these equations. So this means that the first part of the sum is equal to 0. And the second part of the sum is equal to 0. And 0 plus 0 is equal to 0. And so we saw that equation number I is satisfied. But this is true for all I. So this means that every equation of the system of linear equations is now satisfied by the vector U plus V. And so this tells us that U plus V is in the set of solutions. So if we have two solutions of a homogeneous system of linear equations, then their sum is again a solution of a homogeneous system of linear equations. And again, so the property 3 that if U is in U and C is in F, then we need to verify that CU is in U. So this property I leave for you as an exercise. So show that the set of solutions of a homogeneous system of linear equations is closed under scalar multiples. Now, what happens for non-homogeneous systems of linear equations? So suppose we have a system of linear equations Ax equals B, where B is not equal to 0. And so here we have a question. Is solution set U a subspace? And the answer to this question is negative, no, because x equals 0 is not a solution. So if we substitute x equals 0 in any system of equations, then the right-hand side will come out as zeros. And since here we have a system of linear equations with the non-zero right-hand side, so this means that x equals 0 is not a solution, so 0 vector will not belong to the solution set. So this means that for homogeneous systems of linear equations, solution sets are subspaces. For non-homogeneous systems of linear equations with the non-zero right-hand side, solution sets are not subspaces. However, there is a strong relation between solutions of inhomogeneous systems and solutions of homogeneous systems. And here, let us state the following theorem. So let AX equals B be a consistent system of linear equations. Well, we require it to be consistent, otherwise the solution set is empty, and so it's not interesting. And let x equals p be a particular solution of this system. So this means that we're given, or we have one solution of a non-homogeneous system of linear equations. Then the general solution of AX equals B, or the solution set, is P plus general solution of a homogeneous system with the same matrix, AX equals 0. Or equivalently, what we are saying here is that every solution of AX equals B is P plus U, where U is a solution of AX equals 0. And as U runs over the set of solutions of a homogeneous system, which is a subspace, in this way we obtain all solutions of a non-homogeneous system, right? And for every solution U of AX equals 0, this P plus U is a solution of AX equals B. What do we need to prove here? So we need to prove two things. So the first thing we need to show is that if P is a solution of AX equals B, and U is a solution of AX equals 0, then P plus U is a solution of AX is equal to B. So this means that if we have one solution of a non-homogeneous system and another solution of a homogeneous system, then their sum is a solution of a homogeneous system, of a non-homogeneous system. And the second part is that if P and Q are two solutions of AX equals B, then there exists U, a solution of AX equals 0, such that Q is equal to P plus U. So this means that if we take a solution of a non-homogeneous system and a solution of a homogeneous system, then their sum is a solution of a non-homogeneous system. And every solution of a non-homogeneous system is obtained in this way. So this is what we're saying. So there are two parts that need to be proved here. Let's give a proof of these two parts of the theorem. So for part 1, so we let P be the following vector: R1 through Rn, right? And so let this be a solution of AX equals B. And so let U be S1 through Sn, so be a solution of AX equals 0. So what do we need to show? We need to show that P plus U is a solution of, again, AX equals B. So, but what is P plus U? P plus U is a vector R1 plus S1 ... Rn plus Sn. So we need to show that P plus U is a solution of AX equals B. So let us check equation number I. So we substitute this n-tuple in equation number I. So we have AI1 times R1 plus S1 plus AI2 times R2 plus S2 plus AIN times Rn plus Sn. Now, what is this? So this sum may be split into two parts. So we can write it as AI1 R1 plus AIN Rn plus AI1 S1 plus AIN Sn. And what did we get here? So here the first sum is the substitution of P into equation number I. And the second sum is the substitution of S's or U in the equation number I. But, so we see that R's will satisfy the system AX equals B. And here, so this is equation number I of that system with the right-hand side, which is equal to BI. Right? So BI will be the right-hand side of AX equals B of equation number I. So this means, since P is a solution of AX equals B, when we substitute R values in equation number I, we're going to get BI. But S's are a solution of equation ax equals 0. And so this means that when we substitute s's in the same equation, the result will be 0. And so thus, this sum is equal to bi plus 0, so it's equal to bi. And so what we see is we see that p plus u satisfies equation number I of the system ax equals b. So we get bi in the right hand side. And so this is this holds for all I, right? So because I was an arbitrary equation, so if it's true for an arbitrary equation, it's true for all of them. And so here we prove the part 1. We have shown that if we have a solution of a system ax equals b and another solution of the system ax equals 0, then their sum is a solution of ax equals b. Let us now show the second part of this theorem, so that every solution of ax equals b is obtained in the way p plus u. All right, so we're proving the second part. So here we have, so let p and q be solutions of ax equals b. So we can write p as r1 through rn and q as k1 through kn. Now, so we need to show that there exists u a solution of ax equals 0 such that q is equal to p plus u. But if this, if we want this to hold, then clearly, so u must be q minus p, right? So from this equality, we conclude that u must be equal to q minus p. So what we need to do, so we need to check that this u is indeed a solution of ax equals b 0. So that u, which is q minus p, satisfies ax equals 0. Now, let us check equation number I. So we have ai1 times, so what's the first component of u, which is q minus p? So it's r1 minus k1 plus ai2 times r2 minus k2 plus ain rn minus kn. Now we split this into two parts. So the one part, the first part is with r's, and the second part is with k's. Now, so we knew that p and q were solutions of ax equals b. And in the first part, we are substituting p in the equation number I of this system. And in the second part, we substitute q in the equation number I of the same system. And so when we substitute p in this equation, we are going to get bi, which is the right-hand side of equation number I. But when we substitute q in the same equation, we also get bi. And the result will be bi minus bi, which is 0. And that's exactly what we wanted to show. So now we see that the difference of two solutions of non-homogeneous system will actually satisfy a homogeneous system with the same coefficient matrix. And so here we proved part 2. So as a result, we've shown that if we take a particular solution of a non-homogeneous system and any solution of a homogeneous system, we will get a new solution of the same non-homogeneous system. And all solutions of a non-homogeneous system are obtained in this way. Let us give a geometric interpretation of this theorem. So if we look at solution set of Ax equals 0, then we know that the solution set is a subspace. And so this subspace goes through the 0 vector, right? So here we have a solution set of Ax equals 0, and it will be a subspace in the space Fn. Now, if we consider a new system, Ax equals b, so now the same coefficient matrix, different right-hand side. And we assume that this system is consistent, so it has some particular solution p. Then what we're getting here is that the solution set of Ax equals b is the set u shifted by a vector v. So what we get here is that this solution set can be written as p plus u. Right? So we take this subspace and translate it by a vector p. And this gives us the solution set for non-homogeneous system Ax equals b. Right? So this new set is no longer subspace because it no longer goes through the origin. Right? So, but at least geometrically, so it's going to be a subset in our vector space which is parallel to the given subspace u and goes through the point P, which is a particular solution. So this is what's the geometry of solutions of homogeneous systems that are subspaces, and solutions of non-homogeneous systems that are these shifted subspaces. Let us illustrate the theorem on the connection between solution sets of homogeneous and non-homogeneous systems with a concrete example. So let's consider this system of equations. So here we have two equations with 4 unknowns. And to make things simpler, I already taken this matrix to be in reduced row echelon form. So here we see that so we have two pivots here. So variables are x1 and x2 are leading variables. And variables x3 and x4 are free variables. So let us write down the general solution for this system of linear equations. Well, what we do is we assign parameters to the free variables. So we write that x3 is equal to s, x4 is equal to t, and then we can express the leading variables x1 and x2 in terms of these parameters. So if we move terms to the other side, then x1 is going to be 4 plus 2s plus 3t. And from the second equation, x2 is equal to 6 minus 2s plus 5t. So let us write down general solution in vector form. So here we take the column of unknowns, x1, x2, x3, x4, and write down our general solution as a column. So it's 4 plus 2s plus 3t, then 6 minus 2s plus 5t, s and t. Next, we separate constants from parameters. So we get a vector of constants 4, 6, 0, 0 plus the contribution of s. So here we can take s out, and inside we get a vector 2, 2, 1, 0. Plus, we look at contributions with t. So we have t times vector 3, 5, 0, 1. So this, what we have here, is the general solution of ax equals b in vector form. And this first vector here, so this is a vector p, so this is a particular solution of ax equals b. So here we get solutions for all possible values of s and t. And if we set both s and t to be 0, then this will vanish, and we just get 4, 6, 0, 0. And this tells us that 4, 6, 0, 0 is a solution of this system of linear equations. So we can call it a particular solution. And what's being added to it, so this part, in fact, so this is a general solution of a homogeneous system ax equals 0. And so this conforms our theorem. So that the structure of the general solution for non-homogeneous system is a particular solution for non-homogeneous plus the general solution of a homogeneous system ax equals 0. And from here, we also see that if U is a solution set of ax equals 0 of the homogeneous system with the same coefficient matrix, so we just take this matrix, only we put zeros in the right hand side, then what is written here is, so what this says is that U is a span of the set of two vectors. So we have 2, 2, 1, 0 and 3, 5, 0, 1. So what is the span of these two vectors? The span of these two vectors, well, there is something wrong here. So it's minus 2s, so this is a minus here. So the span of these two vectors is the set of all possible linear combinations of these two vectors. But that's exactly what is written here. So s times the first vector plus t times the second vector. So these are linear combinations of these two vectors. So we see that the general solution of ax equals 0 is the span. And thus, it agrees with our other theorem that says that the solution set of a homogeneous system is a subspace, because we know that span of any set of vectors is a subspace. And so here we get a geometric interpretation of these solution sets. So for the homogeneous system, so it's a span of two vectors. So here we have two vectors. So one vector is 2, minus 2, 1, 0, and the second vector is 3, 5, 0, 1. And so these two vectors span a two-dimensional, or span a plane inside the, well, our space here is R4, right? So inside R4, we have a plane spanned by these two vectors. And for the homogeneous system, the solution set is a plane that goes to the origin. For non-homogeneous system, so what we have is we take this plane and we shift it by this vector, 4, 6, 0, 0. So now we get a parallel plane which no longer goes through the origin. And so this parallel plane is going to be a solution set of a non-homogeneous system. So the solution set of a non-homogeneous set is a subspace which is shifted by a non-zero vector. And so here, both solution sets geometrically look like planes, but one plane goes through the origin and the other plane doesn't go through the origin. And those planes that go through the origin, those planes are subspaces. And planes that do not go through the origins are not subspaces, because a subspace must contain a zero vector, right? And this does not. And so what we get here is we get a picture that relates solution sets of homogeneous and non-homogeneous systems of linear equations.